Great. So I'm going to kick off the afternoon session with John Lambert. I think what is the quote? Like, go for it.
Okay, I got a nickel every time. So I was defenders thinking lists, attackers thinking graphs. As long as this is true, attackers win.
And I keep getting customers, so thank you, John. So with that, go for it.
That wasn't part of the quote. Okay, thanks, Leo. Thanks, Leo, for inviting me here. We did some blue hats together and some other things. One of my favorite quotes is, if you want to go fast, go alone, but if you want to go far, go together. And I always like coming to events with defenders and builders and creators and makers so that we can build a better future. Don't know if there's any threat actors here, but please identify yourself. And then, as I said earlier, I've been at Microsoft for 25 years in security, so this year that's half the company's life, but 100% of the cyber, I assure you. And what I thought I would talk about today are graphs, attack graphs, and what I call the algebras of defense. So I'm going to see if I can get Leo to say algebras after this. So a decade ago, when we started building our cloud and customers started onboarding to our cloud, their adversaries followed them into our cloud. And so every month when we celebrated a new customer in a new geo or vertical, new threat actors came to Microsoft. And we had security teams. We had security teams in Windows, in Office 365, and Azure. But we didn't have a security team focused on the adversary. And so 10 years ago, I started the Microsoft Threat Intelligence Center, a Mystic team, in order to have a security team focused just on threat actors and what they're up to and what they're doing. And over the course of time, what I learned from threat actors, to stop a threat actor, you have to think like a threat actor, and that's what led me to graphs. And that's where that quote came from and whatnot, because hackers are always pivoting. The byproduct of a digital infrastructure that you're building piece by piece is a directed graph. It's a directed graph of credentials, it's a directed graph of dependencies, and threat actors they enter your graph somehow. Maybe that's phishing, maybe it's you have an unpatched something out there. They traverse your graph through hacking around, through the secrets that you have, the lateral movement that's there, entitlements, and so on. And then if they're good enough, they can create new edges in your graph because they can exploit zero-day things and write zero-day exploits for things. And so part of what I want to talk to you about today is why I think attack graphs are especially useful in the world of defense, but also they're not enough by themselves. To defend your attack graph, you need the algebras of defense. And so with that, let me move on. Okay, there we go. I'll blame that one on Midnight Blizzard. And so there's no better threat actor in the world that I think exhibits that kind of graph thinking like Midnight Blizzard, which is the Russian SVR. And over again in their attacks, you will see them use this kind of graph thinking where they think in terms of traversal paths, chains of trust, and transitive access. Their primary targets are governments, military, defense, industrial base, like you would expect from a nation-state threat actor. But the biggest wedge in their victims that they go after is information technology, because that is the wedge, that's the sector that if you compromise it, gives you access to all the other wedges of the pie. This was the actor behind the SolarWinds in supply chain intrusion. They've gone after cloud service providers, identity providers to get to their end customers. They target customer support in IT providers because those customer support have access to their end customer systems and they know they can get there that way. So very much a threat actor that thinks in this kind of graph type of thinking. We had an incident at Microsoft with Midnight Blizzard where over a year ago they found some legacy test infrastructure. We're able to compromise an admin in that test tenant, but that application in that test tenant had a very powerful permission to our corporate network, and they leveraged that in order to get access to our corporate systems. And that was Midnight Blizzard. Clearly, when we analyze it, we go, they built an attack graph. And they set about trying to get to some objective using this attack graph that they built. Now, that's a Midnight Blizzard. You may say, John, you may have a midnight blizzard problem, but I don't have a midnight blizzard problem. Like, I don't have that kind of problem. So I'll also give you another example of something a little more everyday that we see. So this is a file checked into GitHub, and this is under one of the Azure quick starts. And so this was like somebody producing documentation on how to call Azure, and they checked in this config file. And what's in the config file? Also secrets for their thing. And so, believe you me, people are checking in config files to GitHub every single day that have secrets leaked in them. And so the question is, what happens next? This is not a secret to some production system. This is some demo environment. But what happens next? Well, I started looking at data like a number of months ago, and I part of what I was doing at the time was, let me just look at failed logons to privileged accounts. Like you can, if you look at successful logons, obviously that's going to happen benignly. Maybe some of those are hacks. But look at failed logons. Who's trying to log in and what's going on with that? And I saw this pattern of logon where you're seeing logon failures with invalid client secret because they don't know the password. But in all the cases, the user agent was TruffleHog. Now, how many, raise your hand if you've ever heard of TruffleHog before? Okay, a few. I had not heard of it at the time. And what is TruffleHog? TruffleHog is an open source tool for the security community. It does two things really well. One is it can scour all kind of repositories to look for secrets. So it can look through S3 buckets where you might have secrets. It can look through GitHub repos. Look at all those things down there for things that might be cryptographic keys, passwords, SSH keys, you name it. And then the other thing that it can do is, it has an enterprise version, of course, but the other thing it can do is, if you have a candidate secret, what you really want to know is it live? Like if a secret that's dead, it's not that useful. So it has, because it's open source, it has 800 different detectors that will try 800 different services to see if your secret is live. One of those is Entra, and so we get to see the case where if anybody tries to log into Entra with a user agent of TruffleHog and it works, somebody leaked a secret out there, right? And if you wonder what does that ecosystem look like, and I'll tell you why here, this project I would say got very well known in the fall. This was another case where a Microsoft employee wrote a test app and just trying to learn, put it on GitHub, leaked their secret in it, and 26 minutes later, it was scanned with TruffleHog. That's how quickly they committed something, and then somebody found that. And so just know that, especially on places where people are checking in source code and publishing those things, like people are checking commits with automated scanning tools for sure. This is what the universe of TruffleHog looked like when I diagrammed it. So I turned to graphs because I didn't even know questions to ask yet. Like, what does this universe even look like? I didn't understand the phenomenology enough to know what to go look at. And right away, you start to see structure in it. And so, for example, there were a lot of clusters here where maybe these are little solar systems. I don't know, this is like the Hubble Deep Field, I feel like almost, where you have TruffleHog from one IP scanning a bunch of apps that belong to one customer. And that could be a threat actor, but that just could be the security team of that customer. You have other cases where one IP is scanning many different applications that belong to many different tenants. And so that's either a threat actor up to no good, or that is some hosted infrastructure that could be running like something that people are checking stuff into, like a GitLab instance that's hosted or who knows what. And then if the infrastructure is hosted on Azure, we get to x-ray through and understand what is this nature, where is TruffleHog running on Azure. And so whether it's a midnight blizzard or it's a TruffleHog, each action in the world of cyber defense has a reaction by the defenders and then a hardening step they can take. And so if they compromise application secrets, you can roll those secrets, or you can get away from developers having hand-rolled secrets for those things and turn to managed identities. Each kind of attack pattern has an attack and defense aspect to it. But notice I've expressed all of these things in terms of what they look like on a graph. Each attack or action has a way to represent. Each defender response has a way to represent that in the graph. And that's why I kind of think, one, every organization has their attack graph, which is created by their choices in technology, created by their choices in their topology of how they roll things out, their two factors, their entitlements that they give, permissions and roles they give to things. That creates their attack graph. It's different for every organization. But I also think the attack graph is one of the unifying paradigms between the attack world and the defense world. I'll say a little bit about how to build attack graphs. One is, I'm a believer that there's no one Uber graph in the sky. You know, it's a graph of graphs world. And so you're going to have a graph from your identity systems. You're going to have a graph of your assets, probably from, wherever your resources live, a graph of that knows about what communications are happening on your network. You're going to have a threat intel graph. You're going to have an incident graph. And you're going to work in projections of these graphs to solve specific problems. You're not going to view the whole graph at one time. I kind of believe any sufficiently large graph is no different than a hairball. Like if you look at it, and so you're always going to be dealing with projections, and your tools are the thing that let you get the right, projection. And if you want to build your own attack graph, there's a lot of things to get started with these. This is an open source project that understands AWS technology called Cloud Mapper. Out of the Lyft company, they built a tool called Cartography, which can build attack graphs out of Azure or AWS. Illumio is a company that specializes in network communication patterns to build network communication graphs. Olaria is another company that specializes in permissions and sort of the entitlement graph of who's got access to what, and nested access and so on. And then there are many tools that help you already identify attack paths. So like the OG tool in this area is called Bloodhound by SpecterOps. Huge shout out to them and the pioneering work they did, especially studying Active Directory on-prem networks, and they extended it to Azure AD as well. Wiz has a lot of attack paths in there, and our equivalent for Microsoft Defender for Cloud diagrams attack paths as well, because attack paths help optimize things for defenders, because defenders don't have enough calories to spend defending everything they have, and they need things to optimize. And you should start with what attackers can do to you. Maybe there's things that you need to worry about that attackers can't do to you. You should worry about what attackers can do to you, and attack paths help on that. And then there are also threat intelligence graphs. Microsoft has one. There's a really interesting company called the Vertex Project, and their tool Synapse, used by many cyber threat analysts across industry. And I would say is a graph native way to do cyber investigations. And then of course the virus total graph as well. So all of these things are almost different layers in your graph. And I think, you're going to end up with a graph of graph approach where you have some security graph that is really informed by the assets and resources that you have that make up your digital estate. And then within that, a subset of that is going to be your attack graph, the attack paths that tell someone how to get from point A to point B and which things are possible traversal paths. Because if you think about you could have a database, and that database could have cookies in it from sessions or users or whatnot. Those cookies are secrets sometimes that allow you to authenticate to other things. And so that's the security knowledge that can find and develop new edges in your graph. And then you'll have your incident and your threat intel graph. And we have an attack graph at Microsoft. This is, at the time, at 400 million nodes and 1 billion edges, and you expect it to be big in a company like Microsoft, and it is. But the thing I would point out is, look at the types of entities that are in there, right? It's not just the size. 100 different types of nodes, like an Azure Key Vault. A database could be a node. And think 200 types of edges that are in there that are all the different relations between things, right? And then, of course, many, many properties. So that's the attack graph. And then the other part that I'm going to switch to talking about now is build the algebras of defense. And so let me explain what this is. So if you're a defender, and I would characterize myself as a defender, I've looked at many logs in my career. That world of defense is 98, 99% of, you look at any defender anywhere, they live in a tabular world. They live in the relational world of Splunk or Cousteau or KQL or T-SQL or something like that. They live in the relational world. And in that relational world, they have operators that relational algebras give them, like select, join, filter, project. Those are the kinds of questions you can ask over relational systems. Super effective, great, and like I said, used for many things. But there are other algebras out there. There's other ways to represent security data that if you do, you'll be able to ask it questions you cannot easily answer in a different algebra. And so we talked a lot about graphs so far. Hopefully many of you are familiar to some degree with graph databases, but once you build a graph, now you can ask questions like, is there an attack path? Let me understand if there's a way to get from this node to this node through these nodes or through these properties. Security people often talk about things like blast radius. Oh, they got to this, they compromised this secret. What's the blast radius of that? Let me look at the degree of a vertex. All of these things you're talking about graph operators in here. The next one, the next algebra is the algebra of aggregates or anomalies. If you know where the threat actor is and you have an IP address, just use a relational query. Where IP address is 1234, you're done. Or the user agent is something hinky, you're done. If you don't know, if you don't have hard selectors to go on, then you're in the world of anomaly analysis. You need to know things like what is normal, what is abnormal. Let me cluster these things together based on these facets. Let me see the outliers of these things. Now you're in the world of distributions, you're in the world of z-scores and things like that, and you're in the world of aggregates. And I'll say more about this later, but like, if all you had were resources in your security graph that you cared about, you could build a graph from that. But the second you want to pull activity data, like sign-ons, resource access into a graph, that data is way bigger than your resource data. Like it is many orders of magnitude bigger. And so but you need it to get new edges. So what you're going to have to do to get it into your graph is you're going to have to summarize it. You're going to have to de-dimensionalize it anyway. So you're going to live in the world of aggregates in order to get activity data into your graph. And now you start to see the algebras work together. They are not, one is on, tab 1 of your browser is relational, tab 2 is graph, and so on. They're designed to work together and contribute to each other's thing. And then the last algebra is vectors. And so vectors, like if you live in the world of AI at all, you can't get too far in it without hearing about embeddings or about tensors. And a lot of that world is built on basically matrix algebra. And the example I'll give you here where vectors are meaningful in a security world is if you can translate your security question to a domain where distance is a useful way to get an answer, and I'll show you an example of that, then now you can use things like cosine similarity and distance metrics. And so, okay. So relational. Everybody knows about the relational world, right? This is your Splunks and your KQLs and whatnot. So, one of the people I learned is this guy named Dr. Edmund Locard. And so everybody's seen a detective show where there's, the detective and they're gathering the evidence to crack the case. And you go, well, who was the first detective? This person who lived in the 1800s was the first criminology who came up with the idea of forensic science. And basically said, look, when there's a crime, there's going to be a bloody footprint, there's going to be broken glass, there's going to be these things. And that is evidence. And if you can find that evidence, it does not lie, you can study it, it does not change, et cetera, and you can crack a case if you can use evidence, and that was the beginning of forensic science. And so his phrase was, every contact leaves a trace. Every contact by a criminal. Now, he didn't know about cyber at the time, of course, but the same thing is true in cyber. If you collect enough logs, every contact by a threat actor leaves a trace in your system. And that is the world of logs. And to protect anything, you need to gather the data from many different things in order to understand that. And these activity logs that are part of all this thing are very instrumental in the investigation of cyber incidents. And as I kind of mentioned, like to build a richer graph, you're going to need to take this activity data and then de-dimensionalize it in one way to find properties and add properties that still keep the size of your graph containable, but allow you to answer interesting security questions. So maybe you don't need to know every IP address that a user's logging in from. You just need to know the ASN of that, because maybe that grouping is good enough to bucket, like to zoom out from a house to a zip code, maybe that way to do it. And then suddenly if ASNs have reputation, earlier someone was talking about source information about network locations, which ones are more likely to be legitimate versus not. If you can de-dimensionalize data from this relational side, then you can empower other things. Okay, And like I said, this is the world of, Cousteau or Splunk or dashboards and whatnot. So that's the relational world. Okay. In the world of graph, of course, we get new questions we can ask by how we choose to model it with path and blast radius. So, one, of course, the choice in a graph first is what are you going to model for your problem, right? And so I'm a hiker. You can't live in the Northwest it took like 6 years for the Northwest to put the hiking hook in me, but it did. And so, if you hike, you can use many different maps. This first one on the left is, I hiked part of the section of the Pacific Crest Trail. It was 70 miles. And there, you know where you're going. Like, you're not, going off into the random wilds. Like, you're staying on the trail. You need to know where can I camp and where is water, so I make it to the end. And so that's really, this is using a certain map for trail navigation. The one in the middle is, I want to go to this ancient backcountry area that I read about in like some mountaineers' annuals from 100 years ago that nobody goes to anymore. There's no trail to it. There's a trail that gets you close, but there's no trail that gets you to it. So there you need a topo map, because you're going to be going up, you see these gradient lines, steep stuff. And you want to know the path of gentlest ascent up there, to get there, in the easiest possible way. And then obviously if you want to get to the trailhead, you want to know traffic and stuff like that. And so just like you need to know the kinds of, what the question you have dictates the kind of graph you're going to build. Same thing in security. So this is that TruffleHog graph on the left. So sometimes we build graphs just to understand, like, what are we looking at here? What is the phenomenology going on? I need to zoom out before I zoom in. The middle graph was an attack path on a constrained part of the system, and we wanted to know, can you get from this thing to this production thing or to this other environment you shouldn't be able to? And you can see the number of different colors on the dots, and that comes because when you build attack paths, you need many different kinds of entities and relationships there. A VM, a key vault, a subscription, like all these different parts that actually connect an attack and make an attack path from it. You're going to have many different relationship types. And then, to analyze attacks, you may need to go see correlations and causations and so on. So at Microsoft, I spent a fair amount of my time educating people about like improving the graph tools that we have, and also popularizing graph thinking with investigators. So, these slides you'll see here are some of those education sessions. But I always tell people, if you want to start thinking about graphs, when you look at a graph, you see the nodes. But actually you need to think in edges. That's the most useful way to start thinking in graphs. If you start thinking in nodes, you're gonna get stuck a little bit, because you know the nouns, but what are the relations between them? That becomes the kind of graph you're going to create, is dictated by the kind of questions you want to ask it, and it's the kind of edges you want to put in there. And then this is just showing people how to build. Once you build a graph, you can run graph queries on it. And then these are different incident type things that we're investigating with these graphs and using them sometimes to summarize after the fact for communication purposes, in some cases to understand the linkages that are maybe hard to get through if you only live in the tabular world. And then we look at how many people are using these things and doing these things and try to figure out how we can improve the know-how in the team as well. Okay, so aggregates, let me get to that. So aggregates are the world of cluster, deviation, pattern of life. And so this is some activity that represents normal at the top. You can see like a workday effect of a Monday through Friday, and drops on the weekend. And then all of a sudden this weird thing starts at the bottom that's highlighted. And this was part of some red team type attack that is hard to do. I would say at the time it was hard to find through a traditional tabular way, because this wasn't some tracked threat actor like we study, like the Midnight Blizzards. They were coming from novel infrastructure, and it would be difficult to find it from a threat intel perspective. But from we understand what the pattern of life of this application is. The volume, you can see over here, the volume of things is 1 million, 2 million, 3 million. This is some production service kind of thing running, right? And then you see something small that starts. And threat actors, they are going to deviate from how your normal infrastructure works. They're going to deviate from where they come from, so deviation in origin or location. They're going to deviate in the volume that they do, that credential or secret normally does, because if it's something for a system, that's going to happen in the zillions. and then they're going to deviate in how they use that credential across resources, because what they want, they're not trying to do the same thing the user or the service is doing. They're doing something different. And so that's the world of deviation. And so part of this goes from taking raw logs and then building summarized views of them across, how often does this service principal use this user agent, come from these ASNs or locations, and building these different anomalies so that we can study them for outliers. And of course we can, if you just build anomalies, you'll have no shortage of anomalies, right? And that's not what you want. But anomalies on attack paths, anomalies that are coming from ASNs that are less reputation. This is where you start to combine these techniques together, and you can find things that are hard to find with just one thing. And these are just some examples of kinds of anomalies that we are, computing or looking to compute across many different dimensions. Like behind every TTP of a threat actor is a pattern underlying that, and you can build aggregates and anomalies to help you identify these kind of patterns. The other thing I would say is the world of aggregates and anomalies, it really is a great big data problem, because investigators want data hot in order to investigate it. They want it in Splunk or Cousteau, and they want it very quickly available to them, but that also has cost. And so you may have some limitations on what's the retention period of that. Is it 30 days or 90 days or 2 years? And so what you might keep in your cold store where it's cheaper, this is where you can do, of course, even in a relational query language, you can summarize and build aggregates on the fly, right? But that's not possible to do at arbitrary scale. And so this is an area I think there's a complement in using batch jobs that are running on cold storage versions of logs, like nightly, say, computing these things, but also, and then saving the results of those aggregations and pushing those into hot, so they are immediately available to people. Then you don't have to keep the full data in there. You can keep the summarized data. Okay, and then vector. So how many of you have heard of anybody talk about AI and say cosine similarity? Okay. I heard it and I said, what are you talking about? Cosine to me was SOHCAHTOA, in geometry. And so I'll give you this is not an example, but it's like a kind of example, which is, imagine you wanted to find a threat actor anytime somebody that they authenticated from a certain location on the globe. So let's just say the threat actor is in Seattle. Well, if you know that and you're worried about anytime they come, there are geo enrichments for IP addresses, and you could say anytime the geo says it's Seattle, then that's something I want to look at. But nearby Seattle is Bellevue, there's Renton, there's Kirkland, there's a whole bunch of places, and you may not know about all of those places for a given threat actor location. So what you really want to know is distance, how far. Like they are within some neighborhood of Seattle. And so you can geo-enrich IP addresses and get latitude, longitude, and then you can project those on a map. And then if you'd look at these, the two vectors there's one pointing to the threat actor primary location, say, and another one pointing to their secondary location, that geographically they're very close because they're going to a remote office or something like that. And if you got a login from, say, Paris, that's nowhere near where they are. And so if you think about the angle between those two vectors, for the ones that are close to your primary location, the angle between them is going to be small because those vectors are pointing to locations on the globe very close to each other. And the cosine of an angle when it's small is close to 1.0. So that's why they talk about cosine similarity. If in the vector space they are close, the cosine of the angle between them will be close to 1.0, which will not be the case for this angle between primary and Paris, France. And so that's the idea of taking some security data, like an IP address, representing it in a metric space where distance becomes something you can make a computation on. And while this is 3 dimensions, because it's like a globe, obviously in security you really want to represent 60, 200, or 1,000 dimensions of data. And so if we go back to TruffleHog, let's say we want to find TruffleHog that does not identify as TruffleHog, because that would be people being sneaky, that they still are exhibiting TruffleHog-like behavior, but they're not identifying as TruffleHog. And so, this is like using GraphSage and things like that, and to go build, a plot of the blue ones are, this is where the legit self-identifying TruffleHogs are. The gray is everything that said it wasn't TruffleHog, and then you can go start trying new logins you're seeing that aren't TruffleHog against it. And anytime you see like a red dot, which are these new candidate ones, in this embedding space that are close to the same behavior as a blue dot, which is a TruffleHog one, that means in embedding space, your representation, the algorithm thought they were close in behavior. And that would be a candidate one to look at, as opposed to one that just looks like all the other gray dots that are out there that are the normal benign activity. So it's just an idea of how you can use the world of embeddings or vectors in order to translate a security problem where you don't have maybe a hard selector to go after, where you could easily do it in a graph or relational or whatnot, and translate it into a security domain where you can use these operators to help you answer questions. And so, this is another area where you get to stand on the shoulders of AI, because all of AI is really built on embeddings underneath the cover, and they have taken models of text and turned that into embeddings. But of course, they have ways to turn graphs into embeddings and all of these, multimodal things. So, and so if you look kind of like, if I were to sum this up here, what I would say is the four algebras are the idea of representing your security data in the different in these different algebras that are here, for the kinds of answers that you can get from them, so that you can use the right algebra for the right security question to help you answer your things across them. And then, if I had to summarize here at the end, I would say, one, don't have an attack graph for your organization. I would go build one. And I would take a graph of graphs approach. For these algebras, I think, one, it's helpful to pick a unifying language across them. That could be Splunk. It can be Cousteau, it could be Python, it could be some domain-specific language. But what you don't want to end up is a world where when you want to do graph, you go to one tab, but when you want to do relational, you go to the other, and you can't mix and match them. You want to be able to operate across them. And then just because you can answer a question in a graph doesn't mean you always want to have to do that. And so each of these algebras can compute answers that you can project back into the other algebra and save it. So you don't have to constantly traverse algebras. And that's like, you can compute aggregates and save those aggregates back and push it into relational, so it's just available there. And then the other thing I have to say, there was not a ton of AI in this talk. You're welcome. But the thing I would say about AI is I'm not sure we're going to get a breakthrough in AI for security by feeding it a huge diet of logs. There's too much structure that those logs don't know about, that analysts do know about, and I think it needs that structure. I don't think it can infer it all from a poor diet of logs. That's part of what, now imagine it had a graph, and it had an attack graph of your digital infrastructure. Now imagine it could ask graph questions, it could zoom out and look at anomalies. So I think while this work helps defenders just do their jobs better, faster, et cetera, I also think, if AI can think in 4 different algebras instead of just one algebra, I think that'll also it'll pay a dividend there as well. So, thank you.
Thank you, John. And I'll kick it off with a question from online, actually. So in this graph of graph worlds, how do you think about pick any of these? There's multiple here. Either time,
and then build a graph from that. Like the infrastructure is changing every day, but I bet you the core attack paths in your infrastructure are probably not, changing every day. And so some people do an approach where they snapshot. Other people essentially bin activity together, like 6-hour windows or 12-hour windows, and then the edges are essentially time locked to those things. And so if you want to do some analysis You can look at time sequence. Sometimes the other reason that could be valuable is normal users have a work day that they work, and threat actors often are not working at the same work hours as them. I'll just leave it at that. And the pattern of life of that. I think also sometimes if you do chunk up things by time, to do it. So, but it's not like they keep some running transaction log per se. That's typically not exactly, the way they do it. But many of these persistent graphs, every edge and every node has a timestamp on it, and they know they can, go to a certain timestamp in compute. Yeah.
Thank you. Anyone? See someone back here. Let me give you a mic just for the people online.
Great talk. Question, if somebody were to bootstrap this graph of graphs for their organization, are there canonical, templates or nomenclature, how you name these graph edges and nodes, or any reference architecture that Microsoft has come up with? Yeah,
so many organizations are going to have security products they've chosen. Those security products probably have some expression of a graph in there. If you use Wiz has a graph kind of thing. If you don't have anything, there are these open source tools. Like if you have an Active Directory, and a lot of companies have an Active Directory, just run Bloodhound. It'll give you an ontology from that. It'll give you attack paths and whatnot for that. I think the big companies, they're going to realize they actually have multiple attack graphs. Like they got the one from Wiz and the one from Microsoft and the one from this. And so some of them are starting to build multi-graph things where they import the nodes and edges from these different ones together in order to help, get the signal out of them that they need. And so I do think that's where that is probably going to be a fairly common thing, unless you can sort of go I'll go all in on one vendor and just go for a best of suite approach. If you can't do that, then you're going to end up having to bring the best of the different graphs and your own data to it.
Right. Maybe one more, and while John answers, maybe. I think Razor.
So John, the really good attacks that we see where we're tracking an AITM attack, they're using Microsoft infrastructure. And when you're relying on Entra for your identity, that makes it a little bit more difficult to track because you have a reputable ASN. We tried downloading the IP addresses, but is there easier way to do that where we could exclude, identity specific individual authentications obviously should not be coming from an Azure virtual machine. I know you guys provide some of that data in the logs and in the Graph API, but is there a simpler way we could exclude any logins from Microsoft Azure virtual machine?
I think the thing maybe to see if we can talk about is if you can attribute activity in Azure down to an Azure subscription, and then you could know that's not mine.
Yeah.
That's the big cheat code right there.
Can we get that built in?
We have enriched versions of that to help us figure that kind of stuff out. Okay. It gets a little complicated with what we call hobo scenarios, where things are hosting on behalf of. So think there's a Databricks in it. Well, that belongs to Databricks. But inside of that Databricks, they're a SaaS vendor, and then it's a workload that has compute that is running for. So that, there is it's not an easy thing, but for basic stuff we have.
Yeah. Also fast flux when they're bouncing around. So that makes it tough too.
All right. Thank you. I guess while we're setting up